everybody, welcome back to the lab. In our last DL, we started to talk about the particle model of thermal energy. But we said that what we did last time wasn't quite enough. We know that thermal energy and temperature are related, but up to this point, we haven't exactly seen how they are related. In this DL, we started working on counting of modes, which is a way of understanding the relationship between thermal energy and temperature. To start with, let's talk about why we need modes. Let's suppose we have a particle in a solid. Particles in a solid, in general, have 6 nearest neighbors, as we've discussed previously. If we add thermal energy to this particle, it will start to vibrate. As we discussed last time, half of the energy that goes into the particle as thermal energy will go into the kinetic energy of the particle, and half of it will go into the potential energy of the particle. We discovered this by considering a mass on a spring and asking ourselves how much energy, on average, would be found in the kinetic energy of the mass or in the potential energy. We discovered that the energy would split roughly evenly on average. So in order to figure out how thermal energy and potential energy are related, let's ask the following question. How many springs do we need to model the vibrations of this particle? We know that this particle is going to start to vibrate as it gains thermal energy. Let's start by asking ourselves if we could model this particle with just one spring. We could imagine this scenario with the particle on the end of the spring. But there's an immediate problem with this model. The spring is only allowed to oscillate to the left and right, but the particle lives in 3 dimensions. It might want to vibrate up and down, or front and back. This single spring doesn't allow it to do that. It turns out we need 3 springs to model the vibrations of a particle in a solid. This is true no matter how many bonds the particle has to its neighbors. Any pattern of vibration that this particle can undergo can be broken down into 3 pieces. 1 vibration up and down, 1 vibration left and right, and 1 vibration front and back. By combining these 3 in interesting ways, we can always model any vibration that this particle would undergo. Of course, the particle is not actually attached to 3 springs, but for a model, it works just fine. We know that in the spring, half of the energy on average is found in kinetic energy, and half of it is found in potential energy. We can think of all these different springs and their individual kinetic and potential energy as buckets that we can put energy in. So how many quote-unquote buckets does this particle have? Well, we know that we're modeling it as being attached to 3 springs, and each spring has a kinetic energy bucket and a potential energy bucket. So the total number of buckets that we can put energy in for this particle is 6. In physics, we call these containers modes. When we add thermal energy to a particle, the energy is going to be split evenly amongst all of its modes. For a particle in a solid or a liquid, the number of modes is 6. It's fixed by the bonds that the particle has with its neighbors. However, for gases, it's not 6, and we'll see in a moment how we figure out how much there are. But before we do that, let's think about what this fact means for temperature. Temperature is a sort of averaging over all modes. When we're looking at temperature, we're effectively looking at a substance and asking how much thermal energy can be found in each particle. The temperature turns out to be related to how much energy can be found in each mode. So what happens if we increase the number of modes that a particle has? Let's imagine 2 particles, one with 6 modes and one with 12 modes. If we add the same amount of energy to each particle, the particle with 6 modes will have more energy in each mode than the particle with 12 modes, because the energy has to be split up equally amongst all the modes in the particles. The particle with more energy in each mode will vibrate more quickly, and its temperature will be higher. whereas the particle with 12 modes will have less energy with each mode. It will vibrate more slowly and will have a lower temperature. So in order to relate a particle's thermal energy to its temperature, we need to know two things. First, we need to know how many modes the particle has. And second, we need to know how the amount of energy in a mode relates to temperature. Let's take a moment to talk about the second piece, how the amount of energy in each mode relates to temperature. There's a theorem in physics known as the equipartition theorem. We've already seen part of it. It says that on average, each mode that a particle has will get the same amount of thermal energy. But it turns out that this amount can be related very directly to the temperature. The amount of energy that each mode in a substance has for a given temperature is given by this equation. Kb is known as the Boltzmann constant. It's just a constant that appears a lot of times when you're doing thermal physics. T is the temperature of the substance. So if we know the amount of energy per mode, we could figure out the temperature of a substance. And if we know the temperature of the substance, we could figure out the amount of thermal energy per mode. Let's do a basic example. Let's suppose we have a substance with Avogadro's number of particles. The substance is at a temperature of 200 degrees Kelvin, and we want to know what the total amount of thermal energy in the substance is. In previous work that we've done in this course, we have very often been interested in changes in temperature. However, now we're interested in the actual value of the temperature, and so we have to make sure we use the right units. When we are working with the actual value of temperature, it is super important that we use Kelvin. When you're doing changes in temperature, it's acceptable to use either Kelvin or Celsius, because a change in temperature of 1 degree Kelvin is the same thing as a change in temperature of 1 degree Celsius. But when you're doing absolute temperature, Kelvin and Celsius are not equivalent, so use Kelvin. So we have Avogadro's number of particles, they're in a solid, and the temperature is 200 degrees Kelvin. Let's start by working out the number of modes that the substance has. Well, we've already said that in a solid, the number of modes per particle is equal to 6, 3 kinetic energy modes and 3 potential energy modes. So if we have 6 modes per particle and Avogadro's number of particles, the total number of modes in the substance is just 6 times Avogadro's number. But we want to know the total thermal energy in the substance. Well, to find this, we just have to multiply the number of modes by the amount of thermal energy in each mode. That number is given by this. We know the temperature, it's 200 Kelvin. So all we have to do is plug in 200 Kelvin here and multiply by the number of modes, and we'll get our answer. When I plug these numbers in, I get 4,984 joules. When you have a solid or a liquid, the number of modes per particle will always be 6. But with a gas, this is not the case. Because particles in gases are not bonded together, we cannot model their movement with little springs. But it turns out that it's fairly straightforward to determine the number of modes per particle for gases. The method that we're going to use here is the closest thing to a recipe that you're going to find in physics. You can apply this recipe to any gas, no matter how simple or complicated. Let's count the number of modes for diatomic oxygen. We'll use this as our model of diatomic oxygen. It's just 2 oxygen molecules connected by a bond. We want to know how many modes an oxygen molecule has if it's in a gas. We start the recipe by counting the number of atoms per molecule. In this case, the number of atoms is just 2. It turns out that any molecule will always have 3 kinetic energy modes per atom. This molecule has 2 atoms, so it should have 6 kinetic energy modes. But we have to go a step further. We need to know how those modes are spread out. When we're talking about a gas, there turns out to be 3 different categories that modes can go into. The first is called translational modes. Translational kinetic energy modes are just modes associated with the movement of the molecule from one place to another. There are always 3 of them, no matter how complex the molecule is. The reason for this is that our world is a 3-dimensional world. No matter how complicated the motion of an atom, we can always break it up into 3 pieces: an up-down piece, a left-right piece, and a front-back piece. The second category that kinetic energy modes can go into is called rotational modes. Rotational modes, as you might have guessed, is just kinetic energy associated with the rotating of the molecule. However, there is a very important subtlety that we have to address. Just like with translational kinetic energy modes, rotation can always be broken up into 3 pieces. One piece that involves rotation around the x-axis, one piece that involves rotation around the y-axis, and one piece that involves rotation around the z-axis. However, it turns out that a mode only counts if that rotation makes the molecule look different. Now, what do I mean by that? Let's say the molecule is rotating like this. You can clearly tell if I go like this that the molecule has rotated. It looks different. It's the same when I rotate it this way. The molecule looks different here than it does here. But what about if I rotate it this way? The molecule looks the same. Any difference you're seeing has to do with the fact that this is just a model of the molecule and not the molecule itself. There is a very real sense in which we could not tell that the atom has been rotated. If this is the case, that rotational mode does not count. This is only the case for linear molecules, that is, molecules that are in a straight line. Diatomic molecules are always linear. They have to be. Some triatomic molecules are linear, but not all of them. And once you get above 3 atoms, you're pretty much always going to be dealing with non-linear atoms. So we know that we have 6 kinetic energy modes. 3 of them are translational, and 2 of them are rotational. So what's the last one? For solids and liquids, the vibrations we were talking about were always vibrations for the entire particle in its relationship to the nearby particles. But in a gas, we're talking about vibration within the molecule itself. This is associated with the fact that the molecule has bonds, and this bond can flex a little bit, just like in solids. Vibrational modes are split into 2 types: potential energy modes and kinetic energy modes. Let's start with the kinetic energy modes. How many vibrational kinetic energy modes do we need in this example? The answer is 1. We've already accounted for 5 of the kinetic energy modes by using translational and rotational modes. So we just need 1 vibrational kinetic energy mode in order to make up the difference. But it turns out that we're not quite done. Every time you have a vibrational kinetic energy mode, you also have to have a vibrational potential energy mode that comes along with it. So because this molecule has 1 vibrational kinetic energy mode, it must also have 1 vibrational potential energy mode. So the total number of modes that this diatomic linear molecule has is 7. 3 translational kinetic energy modes, 2 rotational kinetic energy modes, 1 vibrational kinetic energy mode, and 1 vibrational potential energy mode. Let's do the same example, but with a nonlinear triatomic molecule. The first step of the recipe is always the same. Figure out how many kinetic energy modes the particle has. This molecule has 3 atoms in it, and we know that there will always be 3 kinetic energy modes per atom. So the total number of kinetic energy modes is 9. Let's break these kinetic energy modes up into the categories. The first category is always translational kinetic energy modes. There's always 3 of them, no matter how many atoms you have in your molecule. what about rotational modes? For any nonlinear molecule, the number of rotational modes will always be 3. The molecule will look different no matter which way you rotate it, so the rotational modes will all be active. Lastly, we'll consider the vibrational kinetic energy modes. We know that the total number of kinetic energy modes has to be 9, and 6 of them are locked up in translational and rotational modes. So there must be 3 vibrational kinetic energy modes to make up the difference, and therefore 3 vibrational potential energy modes to go along with them. And there we have it. The total number of modes is 12. 3 translational kinetic energy modes, 3 rotational kinetic energy modes, 3 vibrational kinetic energy modes, and 3 vibrational potential energy modes. By using this information, we can start to determine how the properties of the individual particles in a substance give rise to the properties that we know and love for substances as a whole, such as heat capacity. We'll see that in the next DL.